Hello everyone, welcome to this video. In this video we shall see what are algebraic and transcendental field extensions. So let us get started. Firstly, we shall define what is an algebraic element. An element alpha, which is in the field extension, right? So this is our field F and we have some extension E like this. Now we are taking an element alpha in this extension field. This element in the extension field over F is known as algebraic element if for this element we have some non-constant polynomial in f of x. So corresponding to this we have a polynomial ring over here. In this ring, what we do for this ring, we take some non-constant polynomial p of x. Now this element over here in the extension, if this is a root of some non-constant polynomial here in fx, that means p of alpha is equal to 0. In that case, we say that element alpha to be an algebraic element over f. And what do we mean by algebraic field extension? If suppose this is our extension and if every element here in E that is algebraic over f, that means for each element alpha we find some polynomial over here such that alpha is a root of that polynomial. In that case we say E to be an algebraic field extension. So you see these why the name algebraic has been given to this extension. It is because for an element to be an algebraic element, we must find some polynomial over here in the subfield of the extension field E. So that is why the name algebraic has been given to it. Moreover, let us see what are transcendental field extensions. These are the extensions which are not algebraic. So that means for in these extensions we have elements for that we are not able to find such kind of polynomials whose root is alpha. So we can have an example. So here the extension R over Q, is this a transcendental or an algebraic extension? Now this is a transcendental extension. Why? Because you see this is transcendental because you cannot adjoin some element R to it. That means R cannot be written as some element adjoint to it. This is not equal to Q because in moving from the set of the field of rationals to the field of reals, in moving from this field of rationals to field of reals, we have to add to this an infinite number of irrational numbers. So and so for example we have some number over here, say alpha. For this number we are not able to find some polynomial in this case, therefore this field extension R over Q, this is transcendental, and moreover its degree is infinite because we have to add infinite number of irrational numbers in order to get R from Q. Similarly in this case where we have complex number as the field extension over the field of reals, so in this case this is an algebraic extension. Why? Because you can write C as the field R adjoined by an element I. So we can create this whole field of complex number using two basis elements as we have discussed in the previous video. So for every element over here in complex number, we can have a polynomial in R such that that complex number is a root of that particular polynomial. So for example, for iota, I have selected this polynomial such that iota is a root of this polynomial in R. So similarly for every element in C we can do such kind of thing. And here see here in this case, this is also an algebraic extension, because say for square root of 5 we have some polynomial here whose root is square root 5, and similarly for other elements which are rational numbers, we obviously have polynomials in Q such that they are the roots of those polynomials. So these are the algebraic field extensions. There's also a definition for minimal polynomial of any element u over f, and if you remember, we have also used this result in the previous video. So let us see a formal definition for this minimal polynomial. They are saying the minimal polynomial of u over f, that is basically the monic. Monic means the leading coefficient of that polynomial is equal to 1 and is irreducible. So the monic irreducible polynomial in the polynomial ring of which u is a root, that is known as the minimal polynomial of u over f. Obviously, this minimal polynomial would be the polynomial which would have the least degree of such kind. So the minimal polynomial of u over f is the monic irreducible polynomial in fx of which u is a root. This definition would be more clear by seeing this result. So the result says that if E is any extension field of f, that means we are saying E is the extension field over f, and u belongs to E is an algebraic element over f. That means you can have some polynomial in f. They are saying that is px. So we have some px in f of x be such polynomial of least degree such that u is a root of this. That means we are saying u to be the algebraic element. So in this case, the results are the corresponding polynomial, the non-constant polynomial which we have picked, that has to be an irreducible polynomial over f. The second thing is that if you find some another polynomial in that polynomial ring such that u also satisfies that polynomial, in that case the polynomial that we have selected previously of least degree, it would divide some other polynomial gx. And the third result says that there is exactly one monic polynomial of such kind, that means of least degree, such that u satisfies that polynomial. So from here, can you see the relation of least degree is irreducible and is monic and is of least degree. So that is the minimal polynomial. So from here, the connection between them is clear. So let us move on to prove this result. This is quite useful result. So obviously from here we know that if u is an algebraic element, then this polynomial has to be irreducible polynomial in f. So let us go and see the first part. We have as assumptions that E is the extension field, u is the algebraic element, and px be the polynomial of least degree such that u satisfies p. So now we have to prove that px is irreducible over f. So for that, what we do, if possible, we will prove this using the method of contradiction. So here we have assumed this polynomial as a reducible polynomial over f. That means we can write the polynomial px as a product of two polynomials p1 and p2x, say. So obviously the degree of first polynomial p1x should be less than the degree of the original polynomial px, and the degree of second polynomial should also be less than the degree of the original polynomial px. This is by virtue of definition of reducible polynomials. Now u is the root of px, that is given to us because u satisfies px. Therefore p of u is 0, that means P of u is 0, that means P1u into P2u is also equal to 0. That means exactly one of them is equal to 0. In either case, the degree of each of these polynomials P1 and P2, that is less than the degree of P, and u satisfies this. So this comes out to be a contradiction, because we have assumed that Px is the polynomial with least degree such that u satisfies this. But here we obtained some polynomials of lesser degree than P, which for which u is the solution. So this is a contradiction. That means whatever we have considered was wrong. Therefore, the polynomial Px is irreducible polynomial. This was a quite simple proof. So let us now move on to the second part. The second part says that if you find some other polynomial g of x such that it is also satisfied by u, so in that case our minimal polynomial px that should divide this other polynomial gx. So let us assume that gx be some other polynomial. So gx is also in fx, px is also in fx. Moreover, the degree of px is less than degree of gx, because px is the minimal polynomial such that u satisfies it. Therefore, we can apply the division algorithm onto this. That means whenever you divide the polynomial gx by px, you'll have some kind of quotient polynomial over here and you have some kind of remainder over here. So this is the division algorithm here, and the conditions on the remainder is it should either be 0 or it should be some non-zero polynomial where the degree of this polynomial should be less than the degree of this polynomial px. So in the first out of these two, we can have one as true. So let us see firstly this case, degree of Rx is less than degree of Px. If this is the case, so in that case we have this thing. We can substitute u in place of x, no problem in doing that, yes. Now in the question we are given the another polynomial g that is also satisfied by u, and the original polynomial of least degree that is also satisfied by u. So this quantity is 0, this quantity is 0, so we are only left with r of u is equal to 0. That means when you substitute u into Rx, you get 0. And we also know the degree of Rx is less than degree of Px. Again, we have a contradiction of this kind, because we found one polynomial Rx which is having degree less than Px and it is satisfied by u. So this is a contradiction to the statement that Px is a polynomial of least degree such that P of u is equal to 0. Therefore, in this case we got a contradiction. Therefore, this case cannot be applied. So the only case is that Rx is equal to 0. If Rx is equal to 0, that means we have g of x is equal to p of x into q of x, and from here we clearly see that this px divides gx. So second part is also proved. For the third part, what we have to prove? We have to prove there is exactly one monic polynomial of this kind. So let us assume some another polynomial such that all these conditions are satisfied. So let gx be that polynomial, monic polynomial of least degree, such that u is a root of this polynomial. So from part 2 says that if you have some another polynomial such that g of u is 0, then px should divide gx. So that means we have this result, px divides gx. Moreover, now you are saying, now we are doing what? Interchanging the roles of px and gx. So in this case we are saying gx is that minimal polynomial of least degree such that u satisfies it, and px is some another polynomial. So in this case we get gx divides px. So from here, as both are monic polynomials, being the minimal polynomial. This is given to us, this is monic, this is the minimal polynomial. So these both are monic polynomials, hence they should be equal. So we have exactly one monic polynomial of this kind of least degree such that u satisfies the polynomial. So well, that is it for this video. I hope you understood a little about algebraic and transcendental field extensions. We shall see some more properties of these extensions in the upcoming videos. Thank you for watching.